The last application of Bernoulli's theorem is the sixth one. The sixth one, a liquid flowing out of a vessel. A liquid flowing out of a vessel. A liquid flowing out of a vessel. Let's draw the diagram now. This is the vessel, and there is a liquid filled to this. Let's take the height of the liquid as capital H, and there is a small hole here, and fluid is flowing out from the hole. Let's take the depth of the hole as simple H, and this is the streamline of a fluid particle moving out of the vessel, out from this hole. So there is a velocity at this point. Let's take it as v, and the fluid will move in a parabolic shape. This is actually the flow. Let's mark this horizontal range as x. So if this is simple H and this is capital H, this gap is capital H minus simple H. Let's take base area of this vessel as capital A, area of this hole, small hole, as simple A. Let this point be x, and point here, this point, as capital Y. Okay. Now when analyzing the this setup, we need gravitational potential energy 0 level. So let this be the gravitational potential energy 0 level right now. Okay. Now when we are discussing this theory, discussing equations and all these things about this liquid flowing out from a vessel, there are two cases. One is when this opening is very small, and the other case is when the opening is relatively large. So let's take this case as when the opening is small. When the opening means this opening is small. So when this opening is small, what happens is if we consider velocities at this point and this point, this is a very small hole when compared to this base area. So velocity of fluid coming out from this hole is very high when compared to the velocity of this point falling down. Falling down means when compared to this velocity, a fluid, the velocity for the fluid particle at this place, velocity of the fluid particle, the liquid particle at this place is very small. It is coming down, but it is very small. So we can neglect that velocity. That is one case. The other case, we consider that velocity too. Okay. And now if I apply the Bernoulli's equation to x and y points, it is already written in the theory. By applying Bernoulli's theorem to points x and y along the same line, let's apply the Bernoulli's equation. Bernoulli's equation says that pressure plus half rho v squared plus rho g h term should be constant when considering two places. So here pressure is at atmospheric pressure, plus half rho v squared term we can take it as a 0. Why? Because velocity is negligible at this place. But there is a rho gh term because it is at a height h from the gravitational potential energy 0 level. So this is rho g h equal what is the pressure at this point? This is also open to the atmosphere. So atmospheric pressure is pi plus there is a half rho v squared term here because it has a high velocity at that place. Half rho v squared plus rho gh term is 0 because it is in the same level as gravitational potential energy 0 level. The gravitational potential 0 level goes through this opening, so there is no potential energy here. We can cancel the pi term and then we can cancel the rho term. So we get velocity as, take the 2 here, 2gh square root. Okay. If we know the velocity, if we want, we can write volume flow rate. Volume flow rate equal area times velocity. Area is simple A here. Velocity is this velocity. So this is the volume flow rate. If we need the mass flow rate is rho AV. That means rho AV. That means the mass, the rate of mass flowing out from this opening. After that, let's try to get an equation for this x. So to get the equation for this x, we have to apply s equal ut to this side. There are no any other equations that can be applied in the horizontal direction. Why? Because the acceleration is, there is no acceleration in the horizontal direction. So if you are applying equations of motion, we only have this equation to apply in the horizontal direction, but in the downward direction we have uh, a few more equations. So this is x, this is x. Initial velocity is velocity of this fluid flowing in horizontal direction is v. So it is this velocity square root 2g, and time we don't know, so we have to first find the time. Let's take is let's apply s equal ut plus half at squared in the downward direction. This displacement is capital H minus simple h. Initial downward velocity is 0, there is no velocity in the downward direction, half g t squared. So t is 2 h minus simple h over g and square root. Yeah. So if we apply this to here, I get as 2 capital H minus simple h over g. We can cancel this, and square root 2 times square root 2 is 2. Inside square root I get simple h and in brackets capital H minus simple h. So this is the horizontal range x. By looking at that equation, we can see that range x varies with the depth. Depth means this height. X varies with the depth. Okay. After that, we have now let's consider a vessel filled with liquid up to height h. Same type of a vessel with series of holes made vertically along the vessel. Okay, I will just I will keep this diagram as it is, and okay, now you have to write. Okay, first what you have to write is you have to draw the diagram, and after the line, by applying Bernoulli's theorem, you have to write this section. This is already typed in the note, and below that you have to find the time first and then apply s equal ut and get the range. Okay, now I'm going to erase this part. Let's keep this x equation as it is, and let's draw the other thing that is said in the note. Now let's consider another vessel. Liquid is put into height of h, and there are series of holes made along that side. So let's take one hole at the midpoint, and let's take another somewhere here, another somewhere here, and symmetrically let's take another two holes here. The theory is it says that the longest horizontal distance is covered by the hole located at the midpoint of the liquid column, which is also capital H. So the longest horizontal range is given by the hole at the midpoint of the liquid column. So this gives the longest range. It says that gives the longest range. And again, it says the horizontal range of the liquid flowing from a given height below the surface of the liquid and equal height above the bottom of the vessel are equal. So what it means is the range somewhat some distance some distance below the top and some distance above from the bottom are equal. That means if this horizontal range is uh, to this place, horizontal range of this also, it also comes to the same place. It also comes to the same place, right? So if we are going, when we are going downwards to this midpoint, if we get the highest range, that means this somewhere here, this point should also, it also should have a range beyond this place, right? So the range of this is like this. So equal distance above from the bottom of the vessel should also fall to the same place. So it will be like this. Now if you had a wrong idea like this from your O levels, so somewhere, if you had some idea like this, we know that you know that when going downwards pressure increases, right? When going downwards in a liquid, pressure increases due to the equation from the equation h rho g. So due to high pressure, if you think that this goes the longest distance and these go smaller distances, smaller ranges, that is not correct. That is not correct. It is true that this has the highest pressure, but the time of flight is, I mean, the time it has to come down and hit the ground is small. It is also small, even though this has a high velocity due to high pressure. Velocity is high, but it quickly hits the ground. So therefore it can't go a longer distance. Why? It quickly hits the ground, so it won't be like this. The real theory, the correct one is this. Even though this has a high velocity, it doesn't have it doesn't have enough time for the flight, so it will just hit the ground quickly. This has enough time for the flight because it starts its motion from somewhat a top position, but the horizontal velocity is very small. Therefore it won't go it won't spray out. It won't because this pressure is small, because this pressure because this height, the depth is small. From this equation we know velocity is given from root gh equation. We did it a while ago. So the actual theory is, we know velocity is given by square root 2gh. So when we are going down the vessel, we know the velocity increases, but the thing is, there is no much time for this fluid to fly. So the correct theory is, it is true that velocity is given by this equation. Velocity of fluid flowing out is given by this equation. So according to this equation, simple h is the depth. Simple h is the depth from the surface of the liquid. So when we go deep down the liquid, velocity increases. That means this has the highest velocity and this has the lowest velocity, considering these holes. Even though this has a highest velocity, it won't go to somewhere like this, because it will quickly hit the ground. It quickly hits the ground. Here, of course, it has much time for the flight, much time to move, but the velocity of moving out is very small because of the low depth. So it will quickly turn to the downward direction, and it will just fall down like this. Okay, it will move some small distance to the horizontal, and it will just move at higher velocity to the downward direction. So range is somewhat less. But when you consider a hole at the midpoint somewhere here, there is some considerable depth and there is some considerable distance for it to move down. So the time is also somewhat comparatively high, and the depth, the velocity is also comparatively high. So it will get the maximum range. Okay, you can draw this diagram after, yeah, after all those paragraphs in the 7th page. There is another thing in the paragraph, not the last one, the one before the last. At the end, it says the horizontal distance is covered by the hole located at the midpoint of the liquid column, which is also h. The horizontal range of the midpoint is also h. So can it be like this? Let's apply to this equation. This is capital H over 2 because it is at the midpoint. From here to here also it is capital H over 2. Let's apply to this equation x equal to square root, simple h is the depth. So depth is here capital H over 2 brackets capital H minus simple h is the depth. So simple h is capital H over 2. So here we get capital H over 2. H minus h over 2 means h over 2. Here we get h squared over 4. When you take the square root, we have h over 2. We can cancel it, and so the horizontal range becomes simple h, capital H. So at a depth of capital H over 2, the range is also equal to capital H. Draw only this diagram in the space given. No need to write this. No need to write this. Okay. Now the next one is consider an instance where there are two liquid layers in the vessel. There are two liquid layers. Two liquid layers. So here we have only one liquid, only one type of liquid. Now we have two liquids. Let's take this liquid like this, and the other type of liquid, let's mark like this. Let's take the hole somewhere here. Let's take the hole somewhere here, and Let's take height of this as h1, this as h2, and this is the gravitational potential energy zero level. Gravitational potential energy zero level. And this is the streamline of a fluid particle coming out. So let this velocity be simple v, and this, let's take this point as x and this point as capital Y, and the depth from this level as simple h, simple h. Okay, now if we apply Bernoulli's equation, Bernoulli's theorem is p plus half rho v squared plus rho gh equal k. If we apply it to this x position, x point, pressure at this point is atmospheric pressure plus pressure due to this liquid column. So it is pi plus h rho g, that means h2, let's take this as rho 2 and this as rho 1, h2 rho 2 g. This is the pressure at x, and the velocity at this place is negligible, as it took here the velocity is negligible, so half rho v square term is 0, but there is a rho gh term, rho g, h is simple h, simple h. The height from the gravitational potential gp is zero level, gp is zero level, equal, let's write Bernoulli at this place, this place, this is rho 1, this is rho 1, this liquid is rho 1. Here atmospheric pressure is atmospheric pressure pi, there is no any other pressure, plus there is a half rho v squared term here, half rho 1 v squared plus rho gh term is 0, rho gh term is 0, because it is on the same level as gp is 0 level. Okay, now I can cancel pi here, and I need to subject v. If I subject v, I have to take 2 to this side, 2 to this side, so I will get 2, and in brackets I have h2 rho 2 and plus I am taking g out, so here I have rho 1 simple h, and I am taking simple g out. Here I have rho 1, I have to take it to this side over rho 1. So what I have here is v squared. I need v, so I'll take square root of this whole thing. So this is the velocity. This is the velocity of fluid flowing out in this case. Okay. You can draw the diagram in left top, and after that one line you can apply the Bernoulli's equation. Now we are going to the second case, which is simple B, when the opening is not small. So when the opening is large, now we can't neglect this velocity. So you have to draw the diagram again, And let's mark the velocity coming downwards from this position as u. Unwanted things I will just erase. These things I don't need. Why I needed these things when we are discussing the above cases. I'm not going to use those parts here. I need this velocity, this place, this point, this velocity, and area values, and I don't need this either. Okay, now I'm going to find the velocity at this place. If we have another velocity, normally what we did was using a1 v1 equal a2 v2, we took an expression for this extra velocity, capital A times u equal simple A times v. So u is simple A over capital A times v. After that, let's apply the Bernoulli's equation. So that is already written in the note, applying Bernoulli's theorem to points x and y along the streamline. So when you apply the equation, we get here pressure is P1 is atmospheric pressure plus half rho u squared plus uh, actually this height I don't need. This height I don't need. What I need is this height. This is the height I need. Simple h. Okay. Then I can write rho gh term as rho 1 rho gh. That is the only terms that we have there. Okay, pressure plus half rho u squared plus rho gh. Here we have atmospheric pressure pi plus half rho v squared plus there is no potential energy term. So we can cancel pi first, then we can cancel rho. I need to subject v squared. I'm going to multiply by 2. So I have u squared plus 2gh equal v squared. I'm substituting u squared from these terms. So that is, I have to square this. So what I get is a squared, simple A squared, capital A squared into v squared plus 2g h equal v squared. I'm taking this term to the right hand side. So 2gh equal v squared. I am taking it common. So I have 1 here minus this term, simple A squared over capital A squared. I have to subject v squared. So I will take this to this side. So I have 2gh over 1 minus a squared over capital A squared is v squared equal to v squared, but v equal square root of this thing. So this is the final equation of velocity. Final equation of velocity of fluid flowing out if the opening is large. If the opening is small, we had a very small equation like this. If the opening is large, then we have somewhat complex equation like this. Okay. In the first phase, you have to draw this diagram and write this section, and after that one line you can write the rest. Okay, this is everything related to fluid mechanics in fluid dynamics in mechanics. Actually, fluid mechanics is fluid statics plus dynamics. So statics we have already done, and this is fluid dynamics. With that, mechanics is over. Mechanics is over. Let's do past paper MCQs and questions in another separate video. If you have any questions, you can call me or WhatsApp me. The number is okay. This is the number. You can ask any questions if you have using this regarding this theory or anything. Okay. That's it for today. Bye bye.